Okay, and we're back. Okay, you guys can catch up. Alright, okay. The dissolution process is the part that's going in the forward reaction where you're going from your solid state to your ionic states or aqueous states. So down here, you would have aqueous and aqueous. And then, well, let's see what else is here. The reverse process is going to be the precipitation reaction. So when I say dissolution, I mean dissolve. Precipitate means go back to the solid state. So how could I force it using your Le Chatelier's principle kind of knowledge? How can I force it to go back to solid state? Okay, I could, well, no, actually that wouldn't work because removing the solid's not part of the K, so it would not cause a shift back. Add more of these ions, right? So how can I do that? Could I add to the reaction vessel? Which salt? Adding more lead to iodide?
Yeah.
Okay. It's only going to reach the saturation point, so maybe not. Because this is a solid, like I just said, adding a solid is not going to cause more to dissolve because the solid is not in the K, so it's not going to affect equilibrium when you add it. It's not in the equilibrium constant. Pure solids are not.
Decrease volume. Is that what we're doing?
You could decrease volume of the solution. It could maybe cause a difference. I'm thinking like, how can I add more lead to? How do I add lead to? I can't add just that ion.
You can take away water.
How do I add more lead to? What of these could I add? Lead to nitrate. I could add more of something with that common ion. So we talked briefly about the common ion effect a couple days ago, but anything with a common ion between this one or this one, if I add that reactant or just that solution, it's going to cause a shift. So I can actually add more lead to nitrate, this guy, and it'll shift back towards the reactant side, which will cause the precipitation reaction to occur. So we're going to talk about the common ion effect a little bit more. Pretty much all this is just what I just said. You cool with that? This is just me talking on the board. Yeah. Okay. So what is the K for this? Actually, I'll go back and do the K for this. Maybe. What is the K for this reaction? Ksp equals concentration of the products, which is Pb times I2. I minus R squared. This is not involved because it's just a solid, so it's pure solid, so there's no denominator. That's it. So all KSPs look just like this. You have the two ions it forms. Make sure you put it in the correct exponents and over nothing because you can't put the pure solid in there. So every single KSP will have that kind of format. All right. So these are a couple things we're going to have to be able to do with KSP. So we have to calculate molar solubility. Molar solubility, well, first of all, KSP just means be able to do the concentration of the cation times the concentration of the anion to get to your KSP value. I'll show you how to use the solubility from a solubility curve in a second. Molar solubility is just molarity. Okay, you're gonna have to have moles per liter of the particular salt. Molar solubility of the salt, and I'll show you how we get there. Another one is called just general. It's not molar solubility, it's just what is the solubility without the molar in front. These are the units you would use for that, grams per liter. So if I say molar solubility, you want moles per liter. If we just say solubility, you go to grams per liter. So I've got two examples with that. How are you going to predict if a precipitate will form? What that means is how are you going to predict if it's going to shift left or proceed left? So normally, when you're trying to figure out something's going to proceed right or proceed left, what are you comparing? K with what? Anybody remember that? Q. So if you're trying to figure out if it's going to shift left or proceed left or proceed right, you're going to say Q versus K. If Q is bigger than K, it moves one way. If Q is less than K, it moves the other way. So we're going to use that a lot, but we're going to call Q, it's just a tiny bit different name. What does the KSP represent anyway? Just K in general will represent the extent of the reaction, right? So if we have a really high KSP, that means it's very soluble. Because what that means is that you have lots of ions in the products, which means it's just dissolving and dissolving and dissolving. So you're going to create a large K value because all you're doing is putting the product concentration over nothing, over 1, So it's going to yield a very large K. So the larger the K, it usually means the more soluble. The lower the K, the less soluble. Some of our insoluble products, some are more soluble than others. You guys will do a Ksp lab with this tomorrow, your calcium hydroxide lab. Remember how we kept saying, oh, calcium hydroxide, you ionize it because it's a strong base? Remember that big, like, it's in the gray area thing? Anybody remember that from back in Unit 2?
Yeah.
Okay, so calcium hydroxide is a strong base, but it's not very soluble. But what does dissolve does actually ionize 100%. So that's the gray area one. You guys will do a lab with that tomorrow. But whenever you look at K values, Ksp values, you can compare them only if the ions that are produced are the same in number. So like I can compare calcium chloride and magnesium chloride, because this one's going to make how many ions? How many ions does calcium chloride make in water? Not 2. How many? 3. It makes calcium 2+ and 2 chlorides. So this makes 3 ions. Magnesium chloride makes the same thing. It makes magnesium 2+ and 2 chloride ions. I'm not writing this down, but you should know this, okay? Whereas, oh, I got this right here. Sodium chloride makes how many in solution? 2. Sodium plus and Cl minus. So I can only compare things that make the same number of ions to talk about their relative solubilities. All right, I'll go down. You need any of that? And just a lot of concepts, the verbiage you'll see in some questions. What did I say the SP meant again? Solubility product. Why does that make sense for what our expression is? Ksp is, one of these ions times the other of the ions. How does that make sense with what these words are saying? What does product mean? Multiplied. Okay, so you're multiplying the soluble ions. So it's called solubility product because you're multiplying the 2 ions. That's just like something you probably just want to know. Okay, so here's another example. We've got silver chloride. So silver 2. But silver chloride in a saturated solution, you've got silver. I don't think I have this. Silver chloride solid. That's equilibrating with the ions that it can form, aqueous and aqueous. Okay, so it can do that. In a saturated solution, it's going to go back and forth, back and forth, back and forth, back and forth 100 times. So that for every silver chloride solid dissociated, it's going to make 1 silver ion, 1 chloride ion. But then the silver ions and chloride ions can get back together to reform the solid. So it's dynamic equilibrium because it's constantly going back and forth. So just like any K we talked about earlier, any K is temperature dependent. So a K value is only true for that specific temperature. It tells you it's true for it. Sometimes you'll see that the K value increase the temperature, something gets more soluble. What would happen to the K value if you increase the temperature on this scenario then? Would the K increase or decrease if I said it gets more soluble? The K would increase because it's dissolving more ions. Making more ions would mean that the solubility product would be higher. So you'd have to look at the specific question, but you can get some information if you can look at data to tell me if it's getting more soluble or less soluble. And another thing is that the K is only specified for a saturated solution. So we're going to talk about saturated, unsaturated, and supersaturated. So we've kind of written down some of this already. I just want to specify the temperature part and the fact that this is true for a saturated solution. You guys learn how to take like kind of spotty notes, but they're just shorthand. You don't always have to write every word down. And these values are in your textbook. They'll be given to you unless I ask you to calculate it. Ksp values obviously are very, very small. So most, like in your lab yesterday, you precipitated out silver chloride. When you added the silver nitrate, it was a big white precipitate. That means that this very, 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 very few of those ions will dissolve. That's why that number is so itty bitty. Meaning which side is highly favored? The reactants, the solid part. Okay, I can come back to this in a second if you wish, but those are really two important pieces. Okay, the only other thing here that we haven't talked about is the Q value. So we talked about Q being, what do we call Q back in the day? Reaction quotient. That's just for general equilibrium, we just call it Q, which is the reaction quotient. Sometimes you'll see it called the ion product constant because this is for Ksp, we call it Qi with a little I on it to represent that we're multiplying the ions of a solubility reaction or a dissociation reaction. So in this case, Q would still equal the same setup. It's exactly the same, but we're doing initial conditions, just like we did previously in K, or just normal equilibrium. You do the initial conditions. That's what these little knots right here mean. Just means initial. So what happens here if Q is greater than K, less than K, or equal to K? It's going to do different things, but it's essentially the same concept because you're shifting left or proceeding right. So we're going to use Q versus K to figure out if it's going to precipitate or not. That's all this is really used for in KSP. So if Q is greater than KSP, what does that mean about the ratio of the reactants versus the products? Yeah, so you've got too many products. That means you have too many ions in this KSP problem. Too many ions is not good for a saturated solution. If you have too much stuff in a saturated solution, what's going to start to happen? It's going to be super saturated, it's going to be unstable, and if you disturb an unstable solution, it just precipitates. It just goes away, it just goes out of solution directly to solid. So too many ions means that they need to get together, and they're going to cause a precipitation to occur. And that kind of makes sense because we know that it's like, okay, here's the reaction. And if you have too many products, which way is it going to shift? It's going to shift left, which means it's going to turn to the solid form, which is a precipitate. Opposite of that, if Q is less than K, we have too little products, and in this case, this is too little ions, which means you want more ions to form so that your Q and your K can be equal. I'll go back up, sorry. If you want more ions, you've got to shift which way? Right, so you're going to proceed right. And when does it stop proceeding right? Yeah, when it reaches saturation. So proceed right until saturated. And at saturation point, Q is equal to K. So everything wants, so the initial conditions want to equal equilibrium eventually. So Q and K want to be equal. We got to cause precipitation to occur for that to happen, it'll happen. If you need to dissolve more stuff for it to happen, it's going to happen. It's going to stop once it reaches that saturation point. So give me a term that would describe too many ions in solution. We just said it. Supersaturated. Okay. And then this one would be unsaturated. And then this one would be saturated. I can remember that song. Stupid polar bear song. Alright, give you a second if you should work on that. I've got one more writing song. Oh, I'm starting problems. Alright, yeah, we're good. Alright, does anyone remember any of this from honors chem? Just a little tiny bit. Just at least in the terminology. Okay. And then I think the setup of the questions are easier. It's just you got to know where to put the stuff. So practicing these is really important because I don't want you to see this on the first question on the AP exam and freak out like everybody did last year. So I got a text right after the AP exam that said KSP was the devil because that was the first question on the AP exam last year. So I want to make sure we're thoroughly covering this because this is one of the things that they tend to focus on, which is weird because it's like one 80-80 concept. Okay, this is your solubility curve. You know how to read these. This is in 100 grams of water, which in this case, I think it's potassium nitrate. So like at a specific temperature, let's call it 80 degrees, all you do is you go up to the solubility curve, you look at the temperature correlation, and see how much of that solute, those potassium nitrates, dissolve at that temperature. That's how you read a solubility curve. So sometimes what you'll see is solubility in grams per liter or grams per 100 milliliters of water. And that's what you see on the solubility curve is this version right here. Otherwise, you're doing molar solubility, which we're going to do probably extensively. All right, so did everybody grab one of these question sheets? So you don't have to write down the questions. You just refer to the questions and like write this in your I'm not writing on this paper. I know. That's okay. Anybody else need one? You totally could, but don't. Okay, so I'm going to go through these first couple kind of slow, and then I'll go faster because you'll get the hang of it. So the Ksp for silver carbonate is blah. What's the molar solubility? When I say solve for the molar solubility, first of all, let's figure out what's silver carbonate. Two is over here. Okay, thank you. Ag2CO3. All right, so I want you to, for the first step, is always write down the equilibrium and then the Ksp. So equilibrium is Ag2CO3 equilibrates to what? What ions are forming here? Ag plus, just one plus, and CO3, 2 minus. How many Ags? Two of them. Okay. Because we have a 2 subscript there. We cool with this? This is just dissolving as a solid. Okay. Whenever you're looking at the ratios, for every one of these dissolved, you make 2 silvers and 1 carbonate. So that's a 1 to 2 to 1 ratio. So what you do is, we don't ever do an ice box with the solid part. We only are concerned about the formation over here. Obviously, you're starting off with 0 of both of these, right? Those are your products. How many Ags are you going to form? 2. So I'm going to call that plus 2x. How many CO3s are you going to form? 1x. All right, so this gets kind of like, I know how to add this to 0. So this is 2x and x. So instead of writing out the ICE, this is irrelevant because it's a solid. Instead of writing out ICE all the time, I just go straight to E on these. Because we can say, okay, that's going to form 2x, that's going to form 1x. So to make your questions a bit shorter. Okay, so these are the equilibrium conditions for the silver and the carbonate. So Ksp here is equal to, give me the expression with this stuff first. Concentration of silver squared and... Okay, and then now let's plug in our information here. 2x squared and then x to the first. Simplify this right here. I'm going to wait for the right answer. Think about it, guys. 4, 5. 3x. Oh my gosh.
0.
I love you guys, but 2 squared, x to the first. 2 squared is 4. This comes together to be x to the third. You're going to see this like 100 million bazillion times. Please don't mess that little easy algebra, I don't know what that is, up. So 2 squared is 4, x squared is x squared, and then another x. Remember that you can add exponents. So 2 plus 1 is 3. So it's equals to 4x cubed. Okay, so I'm going to erase this, then I just need some space. I'm going to put 4x to the third right here. All right, so Ksp is equal to 4x to the third. Now, I was telling you about the mole ratios for a reason. Since if you solve for x, that's 1x, right? So for every 1x you form, you're dissolving 1 silver carbonate. So if you can solve for x is equal to the molar solubility. So if you don't understand what molar solubility is, if you can solve for x, you're going to get the right answer every single Ksp problem. So if it ever says for a problem to solve for molar solubility, tell yourself you're solving for x and you're going to be good. Molar solubility just means how many moles of this is going to dissolve. If you know it's 1 for every 1 of something else, which is x in this case, you will be able to solve for molar solubility. So we need to solve for x here. Ksp in this problem was 8.1 times 10 to the negative 12 equals to 4x cubed. Solve for x by doing division of 4 on both sides, and then that number that I have for you. So see, late now I just did it all at one time. Cube root this on both sides, So the cube root of that divided by that is 1.265 times 10 to the negative 4 molar. Sig figs though, 1.27 times 10 to the negative, I can't say what that says, 4 molar. So, oh, is it only 2 sig figs? All right, I believe you. Yeah. All right, so if you solve for x, what did we just say we solve for then? Molar solubility. The other question was to solve for just solubility. I'm sorry, I'm scrolling back up. Just the solubility. What's the units for solubility? Grams per liter. So this is our good starting point. This is molar, which is moles per liter, right? All right, so that's talking about 1.3 times 10 to the negative 4 moles of silver carbonate per liter. And I just want to make sure that you know this is about the molar solubility of the salt, the entire compound. So how do I get to grams per liter? Molar mass. 1 mole of silver carbonate weighs 274 grams. That's going to allow us to cancel out these moles and get us to grams per liter. So once you get molar solubility, solubility is just a single conversion factor there. That is 0.0347 grams. And I think I used my initial number for that. So if you put in your calculator and get something a little bit larger, I used my initial because I didn't want to have rounding error. So if you use that number, you're going to have rounding error. Grams per liter. So notice that number is really, really tiny. In a liter, a huge liter, there's like 0.03 grams of that dissolved, which means it's very insoluble. So most of the time we just assume none of it dissolves. You okay with those two types of problems? Was it so much start there? Yeah.
So, it's like the H2CO3 had a 2 coefficient, but you just want that 2.
You would, but you never ever should put a 2 coefficient in the front. You always want to keep that 1. And you will always be able to. It will be no issue for you. But yeah, you would want to issue those. The next one is really similar to that, so I'm going to hold off on that one. I'm going to do a harder one.
Wait.
Yeah.
Last part of the question says calculate solubility of lead 2 fluoride.
Yeah, that's why I said that next part. I'm not doing that number lead 2 because it's very similar to this same problem. What you would do? Oh, I meant to copy that for number 2. What's number 2 on your sheet say?
Oh,
You always have 2, but
it says the same thing.
I'm going to have to do lead 2 fluoride. Okay, I'm doing this one. I just did that one. I'm just going to skip this one for now. Just go with me on the next one. All right, so, that is hard not to see. All right, the molar solubility of lead 2 fluoride. Tell me the method. We'll go through just the method real fast. Molar solubility, what am I solving for? X. Okay, so that means I need a setup. First step is always to do the equilibria reaction. The second step is to set up your Ksp. The third step is to solve for X. Yes? Oh, my bad. Sorry, that's X. Oh, gosh. I'm looking at my right columns. All right, so we have lead 2 fluoride. Well, that looks like an F. Okay. Equilibrates. That's an X. I lied to you. I'll get back to that. All right, so first of all, always go first set up your equilibrium reaction. Lead 2 plus and F2 minus, 2F1 minus. Whenever you have this, you now can get your K value, your K expression, Ksp, which is what? Concentration of Pb, F minus squared. Okay, you know right now how to kind of set up the pseudo X box here. How many of these dissolve? 1. So it's called 1X, right? How many of these dissolve? 2X. So I'm going to plug in these X values into my expression now. So this is X, and then 2X squared. Let's try this again. What does this equal to? 4X to the third. All right. So if you know that X, though, you know that X is the molar solubility is equal to that number they gave you in the problem. Plug that in for X and solve for Ksp, and you're done. Okay? And I can tell you that answer is 3.98 times 10 to the negative 8. Proper sig figs. for city pigs, that would be, let's see, we're to 360. That's 364. Okay, in KSP, you noticing that I have no unit here, right? All of our Ks have no units. The X, though, is molarity, so that it does have a unit. Yeah.
Part of the problem or
Only your final answer. All right, the solubility of lithium chloride is that. What is the KSP? We'll go through this one fairly quickly. If the solubility is 5.48 grams per liter, I want to get to KSP. What do I need to get before I can even solve for KSP? Molar solubility. So how do I get there? Lithium carbonate. 1 mole of lithium carbonate is some number. That's very important. 73.88 lithium carbonate. So this is going to go to moles per liter, which is our X. That is a number 7.4 times 10 to the negative 2. All right, so now what's my equilibrium reaction? Lithium carbonate, and I hope we all know it's got the 2 on it. How many? 2 lithium, 1 pluses, and 2, 3, 2 minus. They will not give you credit if you do not put the charges on these exam. Okay, because this one's a very special type. All right, so KSP equals what? Give me the expression. Lithium squared CO3. Okay, so all you're going to do is back up to your equilibrium reaction. How many X's is this one? 2X. How many is this one? 1X. So plug those values in here. So you get 2X squared, times X, which is 4X cubed. I told you, you're going to see this a lot, because most things will dissolve into like 2 or 3 ions. So if it dissolves into 2 ions, I mean, you're good at X squared. If it dissolves into 3 ions, you're going to have 4X cubed, like pretty much especially. So then all you're going to do is plug that value in for X and get your KSP. All right, I'm going to go to a harder, oh, I got to do this common ion effect first. All right, this is just a break from problem solving for a second. Calcium chloride, we have our reaction at the top. Calcium carbonate equilibrates to calcium 2 plus and carbonate ion. If I add some calcium chloride, what am I essentially adding? Okay, so calcium because of the common ion effect. All right, so I'm adding calcium, and that's the only thing of interest because that's the only thing in the equilibrium reaction. So which way does it shift? All right, so it shifts left. So what do you see forming? I see a precipitate forming, which is the calcium carbonate. Does the solubility of calcium carbonate increase or decrease when you add calcium? Decreases. So it decreases because there's less ions in the solution, because now you have a precipitate that is formed because of that. So you can affect the solubility of something by adding common ions. That's all the common ion effect is. The effect of insoluble product solubility as you add common ions to that equilibrium reaction. Okay. Do I want to do number 4? Yeah, I do actually, because it's common ion effect. All right. So number 4, the molar solubility of iron 2 hydroxide. What is the molar solubility? So what are we solving for? Okay, so we're solving for X. And a solution that already contains 0.05 molar sodium hydroxide. So we have an initial condition present. Normally you have 0 and 0, both the products, because they're both ions and they haven't dissolved yet. But now we have something initially present. We're going to do the same old, but we're going to actually have to write out the ice part here. So what's our equilibrium reaction here? OH2 yields. Okay. So here's our reaction. We initially have present something. So I'm going to have ice here. Initially we have 0.050 molar of the hydroxide ion, because the sodium hydroxide will dissolve and make, so this NaOH will dissolve to make 1 hydroxide for every 1 sodium hydroxide, so the equation, so the molarity is the same. All right, so same thing though. Start with 0. We don't care because that's a solid. What are we adding here and here? Sodium hydroxide contains the hydroxide ion, which is the common ion of interest to this entire reaction. So I'm adding some totally random chemical, but if it has an ion in common, it's important. So I'm adding X here, whatever here. Adding 2X over here. Equilibrium is just X and then 0.050 plus 2X. Okay, so now we know the KSP. We know how to set it up. Let's set it up first. I'm going to go up just a teeny bit here. KSP, give me the setup without the X's involved. Times. Okay, so then all we're going to do is plug in our equilibrium values because K always is at equilibrium, so you have to use that. So we're plugging in X here and what here? 0.05 plus 2X. Ooh, squared. Ooh, what kind of formula? We're probably going to have to use a solid for this. Quadratic. I don't really want to use quadratic. So what do you want to see if we can do? No. Neglect X. You can neglect X in all KSP problems. I almost guarantee it. Because why? This value is 1.8 times 10 to the negative 15th. Good Lord, that is tiny. So this number is so small that value right there you're adding to the 0.05 is going to be entirely insignificant. It's not going to be useful at all to you. So let's show that. Draw your little arrow through it. Neglect it. Do not neglect this X by itself because it's not being added or subtracted from something. Remember, you can only neglect X when it's added or subtracted from something. All right, so then you're going to get 1.8 times 10 to the negative 15th is equal to X times 0.050 squared. That's pretty easy. Solve for X now. X, what you're doing is just square that and divide it on the other side. I'm not going to show you that math because you're intelligent human beings. You can do that. X is equal to 7.2 times 10 to the negative 13th molar. All right, so did we solve for molar solubility? Yes, we did. So that is telling us that's how many moles, that's the molarity of the iron 2 hydroxide that dissolves in a solution of sodium hydroxide. So if I didn't have sodium hydroxide there, would this number be higher or lower?
Higher.
Higher. Why?
Because there's less common ions.
Right. Essentially, if there's less ion present. So this number is a lot lower than what it should be if it was just in water, just in aqueous solution. The reason why it's lower is because we essentially caused a shift which way? We added a heck of a lot of that. Which way did it shift? It shifted to the left, which would cause more of this to be formed than that little ion right there. So when you put it in a solution of something of its own common ion, it's going to be less soluble because it just can't put any more ions over there because that hydroxide that's already present is taking up so much space. Yeah.
For these KSP problems, we have to do like a 5% thing.
Yeah, I should solve. Well, yeah, I didn't put the math on here, but if you take X divided by 0.05 times 100, I know it's going to be less than 5%. I just don't know what the number is. So you're good. Somebody can calculate that if they want. All right, we already went through this. If you wish to write down more about it, remember though, saturated, supersaturated, unsaturated. If the K's and Q's are bigger or smaller. I don't think there's anything else I want to tell you here. Just to remind you what a solubility curve looks like. Supersaturated is up here, saturated, unsaturated. That's really all. If you need to remember that. We'll go over this a little bit more in the spring with molarity, molality, percent solutions and stuff like that. When we go back to the saturation. All right, I've got 5 and 6 to do. 5's not bad. 6 is a little long. 6 is a FRQ from, I can't remember what, I think it's 1994. So I want to do it. All right, so here's the first one that's a little bit of a doozy. Will a precipitate form? So what do we have to compare?
Q and K.
Okay, so anytime you see that, you're like, okay, I got to get Q versus K. if 50 mils of 0.1 molar lead 2 nitrate is mixed with, oh, oh, with these. I was like, oh, where's the question? Yeah, with this one or this one? So I want you to look at this first one. We're going to do some first, and then we'll do some second. And then you got to get the KSP values from me, the ones that you need. You got to tell me what you need, because you might get a list of KSP values. You got to figure out which ones you need. So what you need to do, I'll do the first one with you, and then I'll let you guys do the second one. You know that you have lead 2 nitrate, and then we have this right here of NaCl. First of all, we're writing out a double replacement reaction. So what's the double replacement? Lead 2 chloride precipitate and sodium nitrate. These should be like second nature to you. Doesn't really matter if it's balanced, because what am I getting ready to do? I'm concerned about only one thing here. I'm concerned about this, and I could do the NIE, but what I'm concerned about is this precipitate that's going to be dissolving a little bit in its little solubility reaction. So I'm going to take that precipitate. I don't want to put that on the solid side here. Equilibrates to lead 2 and 2 chloride ions. So first of all, you have to figure out what the precipitate is, and then you got to go put it through its little equilibrium. All right, so here's the reaction I'm concerned about. How much of this do I have? All I have to do is say I have 50 mils and I have 0.1 molar of the lead 2 nitrate. But once I've mixed that volume with this new volume, I have diluted all concentrations because they're in a larger volume than they once were. So what you do is you take, I'm changing that to liters, 0.50 liters times 0.10 moles of lead 2 nitrate per liter. So I'm taking volume, M times V. What does that give me? Moles. If I take M times V and then divide it by liters, this right here is 0.0050 moles of PV 2+. So I mean, I write lead 2 nitrate for you to show you where I'm getting this information from, but I'm not really concerned about lead 2 nitrate anymore. I only want the ion of interest. And I can do this because how many leads are in here? 1. So for every lead 2 nitrate dissolved, it's also going to form 1 lead 2. So now I'm going to divide this by the total volume. What's the total volume in this reaction? 70. So 50 plus 20. Okay, so divide this by 70 milliliters, which is 0.07 liters. This is going to give me my new concentration of lead 2. That is, ooh, small number. 7.14 times 10 to the negative 2. You do not have to write this in scientific notation. I just have a habit of doing it. Okay, so one initial, I want to put a little I right here, one initial concentration established. The other one is which one that we want to get?
CL.
The CL. Okay, so we're going to take this information, 0.020 liters times 0.040 moles of NaCl per liter. That's going to give me 0.0008 moles of chloride ion. That's because for every 1 sodium chloride, I make 1 chlorine. Divide that by what's my new solution volume? 70 again. So this is a problem that a lot of people forget to do. They forget that when they're doing a mixture, you have to dilute everything to what the new solution volume is. That's going to give us our chloride ion to be 1.14 times 10 to the negative 2 molar. Okay. That's giving us our initial concentrations. Okay. Now, the whole big deal of this was to compare Q to K, right? Alright, so if I have both of my initial concentrations, my KSP, we actually haven't written yet. Using this equilibrium, KSP equals what? Give me the format, the expression. PV squared. Okay, so now that I have those, I can actually use this expression that Q is equal to PB 2 plus initial times CL squared initial. So what I'm going to do is just plug these numbers in for these values here. Lead was 7.4 times 10 to the negative 2 molar. chlorine was 1.14 times 10 to the negative 2 molar squared. When you do this times this squared, you get 9.3 times 10 to the negative 6. Okay, what do I need to compare this to? To K of what? What compound am I looking for? So lead 2 chloride. So that's the K you should ask me for, right? So go use Miss Emma. What's the KSP? The KSP for lead 2 chloride is 1.6 times 10 to the negative 5th. So which one is larger? K is larger than Q because you notice it's 10 to the negative 5th, it's 10 to the negative 6th. Yeah. It's a constant, it's just from a table. You'd ask me for it. So K is greater than Q. So it's unsaturated because we have 2 little ions in solution. So if it's unsaturated, is a precipitate going to form? No, because the Q is less. That means we're cool. There's not too many ions in solution, so we're not going to form a precipitate. So no precipitate forms. So on an AP exam, what it would say, it was predicted if a precipitate would form, use mathematics to support your answer. So you have one of these on your test on Friday. Okay? So I want to go through a big, huge one with you. It's not bad math, though. You just have to remember to dilute first, compare Q to K, and then decide. So it's like a 3-step process. The steps are kind of large, though. Okay. Just briefly tell me the only difference in this problem, so we don't have to do the second one. So it's CaCl2. What does that tell us, though? So you see how I did? Okay, so the KSP value will be, yeah. Well, actually, no, the KSP value won't be different. The value will still be the same because we're still doing lead. Was it lead 2 nitrate? Yeah. We're still doing lead 2 nitrate plus CaCl2. So what precipitate are we forming? PbCl2. So we're still forming the same exact precipitate. But what's going to be different is that, you see this 2 right here on the chlorine? When you take this and you do your big M times V, you're going to get moles of calcium chloride. When you get your moles of calcium chloride, that's not going to be the exact same number of moles of chlorine. Because how many chlorines form compared to the calcium chloride? 2. So what you should do is take your moles of calcium chloride, and you can like divide by volume an hour later, but you're going to say for every 1 mole of calcium chloride, you're going to make 2 moles of chloride ion. Because what happens is calcium chloride makes calcium 2 plus 2 Cl minus. So don't just straight up take the molarity times the volume, divide by volume, and you're done. You got to multiply it by 2 because you can make twice as many chlorines. So everything else is the exact same. It's just your chloride ion is going to be higher. So whenever you plug it into your KSP or your Q value, you do lead 2 and then Cl minus squared. This number is going to be a little higher than what it was in the previous example. Because the values, you can see those values are the same, it's just G double for this one. Okay? Because you've already done half the math for this, I'm not going to go through another one. Can I go to the last one? So close, guys. Taste it. Yeah. Victory. And blood, sweat, stress, and coffee. So, halides, but not heavy ones. Blood that is heavy. Okay. Are you ready for number 6? Yes. Okay. I think I'm spaced. Okay. So at 25 degrees, the solubility product constant KSP for strontium sulfate is 7.6 times 10 to the negative 7. The solubility product constant for strontium fluoride is 7.9 times 10 to the negative 5. So we have 2 different compounds. We're going to be comparing them and talking a little bit about their relative solubilities. Write the chemical equations for the dissociation of each of these compounds. First one. SO4, solid.
SO2
Plus,
plus 2.
SO4, 2 minus. Next one, SRF2 equilibrates to, and
F 1 minus 2
2F 1 minus. Okay, so we're going to have two different types of KSPs because you'll notice we have 2 ions and then we have 3 ions. It's going to be a little bit different between. Write the 2 equilibrium expressions. What does that mean? Write the KSPs. Okay, KSP for the first one is?
R 2 plus
Uh-huh.
and
2 minus. That's it, because there's nothing squared, nothing. Next one is KSP is equal to SR 2 plus times. Okay. What is the molar solubility of SrSO4 in pure water? What's the molar solubility of SrF2 in pure water? What are we swapping for both of these?
Okay.
X. X. We're swapping for X. Okay, so we have the setups. We have these. I'm going to kind of be really like an Evan Alpern here and squeeze some X's up in here. So, how many X's is this worth? 1X and this one? 1X. This one? X and this one? 2X. Okay, so all we're going to do is use these X's, put them here. These X's, put them here. Solve for X. Yeah. Equal? Okay. So KSP for SRS4 was 7.6 times 10 to the negative 7th is equal to this times this, right? So what are we actually putting in here? No.
X cubed.
No.
X squared.
X times X. So we're doing X for the SR2 and then X for the SO4 2 minus, which is just X squared. So you square root that, you square root that, you get X is equal to, I believe you, yeah. 7. I'm just going to write the whole thing out just because I don't want to round too soon. So you should get something like that, molar, and then the exact one would be, what's our arithmetic base? 8.7 times 10 to the negative 4th molar. Alright, so there's our first molar solubility of SR strontium sulfate. Second one, same setup, except what's different here. KSP value is different, first of all, which is 7.9 times 10 to the negative 10. It is. I'm just going to show that work for that, okay? So what am I putting here? X, and the next one? 2x squared, so that's 4x cubed. I'm glad we got over that little hump that concerned me. Okay, so divide by 4 on both sides, and then cube root that. Cube root that. Okay, that gives me a lovely number of 5.8 times 10 to the negative 4th molar. Okay. So that first part's pretty easy. It's the standard KSP stuff. Next parts are thought-provoking questions. So here we go. An aqueous solution of strontium 2 nitrate is added slowly to a 1 liter of a well-stirred solution containing 0.02 moles of fluoride ion and 0.10 moles of sulfate at 25 degrees C. You may assume that the added strontium nitrate solution does not materially affect the total volume of the system. Which salt precipitates first?
Oh, I know.
See, I don't believe that, but we'll get there. And then we're going to see what's the concentration of strontium ion in the solution when the first precipitate begins. Okay, so we have available to us very little information. We have, I don't have enough space. I need myself some space here. What? Maybe, and I'm just going to go like that. All right, so we have available to us the fluoride ion is what? 0.02. Yeah. Moles per 1 liter, so I know the molarity, right? I'm just going to go ahead and put molar there because we divide by 1 liter. What else do we have available? Sulfate is 0.10 molar. All right. I have a little cheat sheet for you. So we know that this is being added. That has a common ion of strontium. This is being added, but we don't really know how much yet because we know we have this ion in solution and this ion in solution. You're going to keep adding strontium, and then eventually either strontium sulfate or strontium fluoride is going to dissolve. how are you going to figure out which one dissolves first? I mean, not dissolves, which one precipitates first? You know the Ksp value, you know the expression is SR2 plus and an F minus squared for this one. And you know the expression for this one is SR2 plus and sulfate for this one. What do you think we should do? How? What do you want to solve for? Okay, so if you solve for this here and here, if you figure out which one is smaller, that means that that tiny bit of the strontium nitrate, or sorry, the strontium will dissolve. If you put any more into it, it's going to precipitate. So if you can figure out which of these strontiums are smaller, right after that point, it's going to precipitate. Okay, we know the value already here, and we know the value already here. Ksp is equal to, what was it on this one for the fluoride? 7.9 times 10 to the negative 10th is equal to SR2 plus, which we don't know, but that one we do, which is 0.20 molar squared. All you're doing is plugging in the information given to you. Yeah. I'm sorry. Yeah. That's an O right there. Okay. So when you solve for this, you're going to square that number and divide. So SR2 plus is equal to 1.975 times 10 to the negative 8th molar here. And I just simplified the math. I just went ahead and went straight to the answer for you. You guys can plug that to your calculator. Okay. And then the K value for the strontium sulfate was 7.6 times 10 to the negative 6. Nope, 7. Alright, so that's given to you in the problem. Set it up equal to SR2 plus times the sulfate ion of 0.10 molar. See that? Alright, so you're just going to divide by 0.1 molar on this side and this side. So you get a final answer of strontium equal to 7.6 times 10 to the negative 6. We could have done that already, but it's just using decimal back. Alright, so which of these is a smaller number? The fluoride one. So the smaller value means, and I'm just writing this up here for your benefit, means that only this much SR2 plus from strontium nitrate will dissolve before precipitation. Now right before like that 18 here. You can do some shorthand there. Alright, so that's going to precipitate first. We already have answered part A, so we know that strontium fluoride will precipitate first. The second part of this question was, what is the concentration of strontium ion in the solution when the first precipitate forms?
We already found that.
Right, done. Part B is right there. So we answered part A and part B at the same time.
Oh, sorry. Which one was it? Ending up. What? Wait. Oh.
If the number was smaller, doesn't that mean you could add more to it without it precipitating out?
No.
Oh, small. Okay.
So that means that very, very, very little will dissolve. And so if you add a little bit more, it's done. Yeah, I'll listen.
Whichever one has the smaller one.
Because the solution can't hold as much. So if you add a little bit more of that strontium nitrate, it's going to precipitate out. All right, I'm done with people. Let me tell you what I need you to do. We have 10 minutes. Oh, we have 20 minutes actually. Awesome. Let me cut